Yeah, today we want to look at algebraic structures. Under algebraic structures, we'll be looking at some of the algebraic structures that we look at would include the groups, rings, and fields. Of course, there are several. We also have vectors and so on, but we will begin with these three, where we'll be looking at the groups, the rings, and the fields. Most of these concepts, we've already covered them. Most of them so they will not appear new to us because we've already covered some of these concepts. So that will help us understand the concepts in group theory, which includes groups, rings, and fields. Now, so why are these algebraic structures important to us? We've said that modern cryptography would then rely on these algebraic structures to do some mathematical, some mathematics that is required, especially in cryptographic protocols, depend on these algebraic structures. The mathematics that are required in these cryptographic protocols. So I've said that understanding these structures, the algebraic structures, and the features will be very important in developing secure cryptographic systems and also in the discipline of cryptography, and finally post-quantum computing. So it will be very important when we come to, we look at more other algebraic structures, not just these three, but we begin with these three, and you'll find that when we come to post-quantum computing, again, you'll find the algebraic structures will be very much important there. So I begin by examining groups. So we'll look at groups today, and then look at groups tomorrow, and then see if we'll not have done with the groups next week. Again, we can revisit, can look at groups. So I begin by the definition of a group. And just before the definition, groups are algebraic structures which are made up of one binary operation. So we need to begin by getting the definitions. What I mean by binary operation in terms of groups. In terms of groups, the binary operation I'll be talking about would be either addition or multiplication. So that is the binary operation. It will be either addition or multiplication. So for multiplication, we would either use this or we can use this to mean multiplication. So what we are saying that a group would consist of only one binary operation. So we cannot have addition and multiplication done at the same time. But some of these algebraic structures, which accept groups, some of them would have these two operations done at the same time. We'll have the two operations considered at the same time. But for groups, we would either look at addition, we will either refer to a group as an additive group or a multiplicative group. So when we talk of an additive group, we'll be referring to a group whose binary operation is addition. And when we talk of a multiplicative group, we'll be referring to a group whose binary operation is multiplication. Now, but before we look at the operation addition, the binary operation addition and multiplication, I would begin by looking at this operation. And this operation that I've written here would mean any of these two. So whenever I use this, I mean any of these two. Some books would use a star. Some books would use a star just to the same as this, to mean any of these two binary operations. So when I don't want to commit myself and talk of an additive group or talk of a multiplicative group, if I want to generalize the group, then I would use any of this, but I'll stick to the first one. I'll stick to the first one. That is when I want to generalize the group. So that if I don't want to talk about addition or multiplication, if I want to talk about properties that are general, properties which cut across, then I'll be using that circle. Now, let's go to the definition of a group, and the definition is here. This is the definition. And I've said a group is an empty set. An empty set. And you know what a set is? A set is just a collection of objects. For example, I can talk of a set of textbooks in a library. Or I can talk of a set of university students. Or I can talk of a set of students doing blockchain. So just a set is a group of things which are well defined. That's what I mean a set. And normally, if a set is A, we list the elements within braces, these curly brackets. That is why we list the elements of this set. So I didn't know what to talk about set. I want to talk about a group, but then I have to define it as a set. So that is why I'm telling a set is just a collection of objects put together. If we have objects put together, then we call that a set. A set which has elements, we say is an empty, so it's not empty. So let G be an empty set together with the binary operation, this binary operation. Then these two put together, the set together, the binary operation, is a group if it fulfills the following properties. So for this set, together binary, and this binary operation I've said I'll be using this circle to mean either addition or multiplication if I want to be general. If I want to be general, then I'll be using this. So, and when I be talking about additive group, then I'll just replace this. I'll replace this operation with addition. And if I want to talk about a multiplicative group, I'll replace that by multiplication. So that is how we be the symbols that I will be using. Now, again, let me define a group. And I'm saying that a group is an empty set together the binary operation that fulfills the following properties. The first property is the property of closure. The property of closure, and what the property of closure means, for instance, if we are talking about addition, supposing I have elements of a set, and let me say that my set is this. Let me talk of my set. Just want to give an example so that you understand what I mean by closure. Supposing I have my set, and let this be my set A, and my set, supposing it comprises of the elements. I've begun with the dots, meaning we have other elements on the left going up to infinity, negative infinity. supposing I have these elements, then I have 0, 1, 2, and so on. What do I mean by closure? What I mean by closure is, if I talk about addition, is that if I pick any two elements from this set, if I pick any two elements from this set and get their sum, the result would be a member of this set. The result would be a member of this set. If that is fulfilled, then we say closure property has been satisfied. For instance, let me pick element 1 and element 2. If I pick element 1, element 2, and add these two, I get 3. And I can see, because of these dots, it means 3 belongs to this set. 3 belongs to this set. So 3 is a member of this set. So it means closure has been satisfied. The closure property has been satisfied. Under addition. And I said this symbol would mean both addition and multiplication. So again, let me talk of another set. Let me take another set. We take another set. I just want to use this set of natural numbers. 2, 3, 4, 5, 6, and so on. Under multiplication, what I mean by closure is, if I were to pick any two elements, 2 and 3, for instance, and multiply under multiplication, the answer that I get is 6, and I can see that 6 is a member of the set N. 6 is a member of the set N. So again, it means the set is closed under multiplication. This set is closed. So that is what I mean by closure. Closure property, that is what I mean. Now, so that is the first property that a set must satisfy for it to be called a group under a binary operation. It must fulfill the closure property. The other property is the property of associativity. Now, the property of associativity, I've said for all elements X, Y, and Z in the set, the binary operation on these two and then on that should be the same as that. So what that means, let me just use addition instead of this. Let me show you what, if I were to use addition, what this would mean. That if I have 3 elements from that set, if I pick any 3 elements from this set and get the sum of the first 2 and then add the third element, the result should be the same as the first element plus the second element plus the third element if the bracket position is changed just like that. So for instance, if I were to use the first set we were referring to, the set of the elements from -4, -3, -2, -1, 0, 1, and 2, and so on. What this means under addition is that if I get an element like -4 and then add to it -3, then add to it another element just from the set, this result should be the same as if I change the position of the bracket, the result will be the same. This is not always obvious for all the sets, but for some sets, this will be true. And so we are saying that if a set has to be a group, this is another property that it must satisfy. And then we have the third property. Of course, it must, for a set to be a group, it must fulfill all the 4 properties. All the 4 properties. The other property is the existence of the identity element. The existence of the identity element. Then the identity element is that element. Look at what the identity element is doing. Supposing my identity element here is E, Look what E is doing. And addition, supposing this was addition, what I'm saying is, if I were to add this element plus G, the result would be G. And again, if G comes first and then add that element, the result will still be G. So that means the identity element is that element that has no effect on the other element in terms of addition or in terms of multiplication. Taking this set as an example, the identity element and addition is 0. So this set has identity element. This set has an identity element, so that if I have -4 plus this identity element, the result will be -4. And if I take 0 plus the identity element plus -4, the result will still be -4. So 0 is the identity element and addition. If I was to take this other set that we referred to earlier, this set 1, 2, 3, and so on, this one we can consider it under multiplication because it does not have the additive identity element 0, but it has the
Hi, Simon. Hi, everyone. I think we lost Mwalim. Let's give him 1 minute.
Okay. Sorry, I think I disappeared for some time. Huh? You can now hear me, is that okay?
Yes.
Okay, so I was to talk about the existence of the universe. Every element of that group, that set should have an inverse. Every element should have an inverse. We've already talked about issues of inverse in modular arithmetic. And so again, we'll again revisit it here. So it makes our work easier. Now, so every element of the set must have an inverse. Under multiplication, under addition, let me begin by addition. Supposing this is a set, and supposing this set has elements -4, let me just repeat that, -2, -1, 0, 1, 2, and so on. These are sets. So we want to check if this set is a group. The first thing we checked was closure property, and we saw that it was closed under addition. Under addition, it was closed, that if you pick any 2 elements and add, the result that you get will be a member of this set. For instance, if I take -3, -2 plus 1, if I take -2 plus 1, the result is -1, and I can see that -1 is a member of this set. -1 is a member of this set. So the closure property has been satisfied. So the other property is associativity. I pick any 3 elements. Let me pick 0 plus 1 plus 2 under addition, and then look what if the result is the same as 0 plus 1 plus 2 with the bracket changing position. Of course, this way I get 3, and this way I still get 3. So that's associativity has been satisfied. Then the other property is the existence of the identity element. I check whether the identity element is there, and I can see under addition, the identity element is 0, so that property has been satisfied. So the other property that we will talk about is existence of the universe. Under addition, the element A, the inverse of A is negative A. So that an element plus its inverse would give you the identity element. The inverse of A would be negative A, so that an element plus its inverse gives you the identity element. So in this case, the inverse of negative 2 is 2. The inverse of negative 2 is 2. And the inverse of 2 is negative 2. And you can see it's there. So every element must have an inverse. And that's why you're seeing that I have dots, meaning that this set continues. So I can see that I have 4 here. I have 4 here, which is the inverse of negative 4. I have 1 here, which is negative 1. I have 5, which is a inverse of negative 5, and so on. So every element must have an inverse. So we can confidently say that this set here is a group, therefore. This set is a group. It has satisfied all the 4 axioms. The first axiom, closure, has been satisfied. And you can see here, closure has been satisfied. You pick any 2 elements and get their sum. The result is a member of the set. The second property, associativity, has been satisfied. And you can see that. The fourth property, the identity element, we can see that the group has the identity element. The set has the identity element, 0 and addition. And then the last axiom, every element has an inverse. Every element has an inverse. Now, what is an inverse under multiplication? Under multiplication, if I'm looking at real numbers, the inverse of 2 would be a half. That's the inverse of 2. So that 2 times its inverse gives you the multiplicative identity element. Gives you the multiplicative identity element. The inverse of 3 would be a third. So that the product of these 2 gives you the identity element. The inverse of a quarter is 4. So that the product of these 2 gives identity element. That is what we mean by inverse of an element. And this is about real numbers. But when we talk of modular arithmetic, again, we know how the inverse now becomes. Of course, what we know is that the inverse of A is B if the product of these 2 is 1. So this is what remains true. Now, so we now know what a group is. A group is a set together with a binary operation that fulfills these 4 conditions. That is what we mean by a group. So that means if you're given a set, you should be able to tell if that set is a group or not. That is what is very important, whether you can tell. So let me look at this set that I was referring to earlier, the set of these natural numbers, and it begins with 1, 2, 3, 4, and so on. The question is it a group? Now this one, I cannot consider it as a group under addition because I can see that there's no identity element under addition. The identity element under addition is supposed to be 0. It's not here. And again, I cannot consider it as a group under addition because I can see these elements lack inverses. The inverse of 4 under addition is supposed to be negative 4, and it's not here. The inverse of 3 under addition is supposed to be negative 3, and it's not here. So it therefore means that this set can never be a group under addition. It can never be a group under addition. One reason disqualifies it. Once you have one reason that disqualifies it, then that it means that is enough. You don't need to have several reasons. Although closure can be satisfied, closure I can see can be satisfied, because if I take 2 plus 3 will be 5, and 5 is a member of this set. If I take 1 plus 2 is 3, and 3 is a member of this set, closure is satisfied. That is no problem. Once I have one reason that disqualifies it, that is enough. The reason I have is that under addition, it lacks the identity element. Under addition, again, I can say that the elements here lack inverses. Now let's see whether it qualifies to be a group under multiplication. Under multiplication, I can see the identity element under multiplication is there. That is the multiplicative identity element 1 is there. Under multiplication, I can see closure is there because if I multiply 2 times 3 is 6, and 6 is a member of this set. So closure is there. But what I'm not seeing under multiplication is the inverses. These elements lack inverses because under multiplication, I cannot see an element which, when multiplied by 4, gives me the identity element 1. I cannot see it. I cannot see that element. So that means, therefore, that this set is not a group under multiplication. It's not a group under multiplication. Now, supposing we have a set that has, let me say like the one we had, this set, we had this set, and this set we said it had elements, negative 4, negative 3, negative 2, negative 1, 0, 1, 2, and so on. And we've said that this is a group under addition. Of course, it cannot be a group under multiplication. This one is not a group under multiplication because I cannot see an element which, when multiplied by 2, gives me 1. I cannot see because 1 is the identity under multiplication. So it cannot be a group under multiplication, but it is a group under addition. Now, so how many elements are here? So the number of elements of that set is what we call the order of the group. If it's a group, the number of elements is what we call the order of a group, and then we denote it by this. We denote by 2 vertical lines. For instance, I'm asking myself, what is the order? What is the order of this Z? And the order of this Z, I can see the elements here are infinite. The elements there are infinite, and therefore the order of this is what I've defined in definition 10. What I've defined in definition 10, that a group is said to be infinite or is said to be of infinite order if it has an infinite number of elements. If it has an infinite number of elements, then we say that that group is infinite. Now, we also have what we call a abelian group or multiplicative group, no, commutative group. Abelian or commutative group. So if I'm asked to define an abelian group, or if I'm asked to define a commutative group, I begin from where we began to define. I say that a group and an empty set G together the binary operation is said to be an abelian group if it fulfills the following 5 axioms. The following 5, the first one is here, the second one there, the third, the fourth, And then now the fifth is what we were reading. The fifth property that a commutative group must fulfill is this. That is the fifth property. So a commutative group, a set has to be is a commutative group if it fulfills the above four axioms plus this extra axiom. What does this axiom mean? What this axiom means under addition, it means that if I have G plus H, the result should be the same as H plus G. Under multiplication, it means if I have G times H, the result should be the same as H times G. So this is not always true. For instance, if you take an example of matrices, if you have a group, if you have a set of matrices, do they form a group under multiplication? Yes, they can form a group under multiplication, but do they form a commutative group? So that is now the question. And the question is, the answer is they do not form a commutative group. For instance, if you have matrix A, which is a 2 by 2 matrix, and then matrix B, if you get this product is not always the same as matrix B times matrix A. It's not always the same. It's not always the same. So that means a group of matrices is not necessarily commutative. For instance, if you have this matrix 2, 2, 1, 3, and another matrix that is 1, 4, 8, 2, and then multiply, the result that you get will not be the same as 1, 4, 8, 2 multiplied by 2, 2, 1, 3. It will not be the same. It will not be the same. Oh, it may not be the same because you can see this would be 2 plus 16, which is 18. This when you multiply these matrices, that will be 16, and this will be 8 plus 4, which is 12. 8 plus 4, which is 12, and this will be 1 plus 24, which is 25, and this will be 4 plus 6, which is 10. So you can see that is what you get. But when we do this other side, this will be 2 plus 4, which is 6. So the first element is already is not the same as this. So matrices are not commutative. They are not the only ones that are not commutative. We have so many other groups that will not be commutative. So in fact, we look at some groups which are not commutative. Then we look at groups which are commutative. So that as we proceed, you know which group is commutative and which one is not commutative or abelian. So what we're saying that a group is abelian, therefore, if it fulfills this fifth condition. That's when we say that it is abelian. Otherwise, if it does not satisfy that condition, then we say it's non-commutative or non-abelian. Now let's look at examples of groups. Examples of groups, of course, we define what a group is. And the first example is the one I was using. The set of integers under addition forms an abelian group. The set of integers under addition forms an abelian group. This is what I mean by set of integers. The set of integers, this is what I mean. These are the integers. That dot, -3, -2, -1, 0, 1, 2. These are integers. That's what I mean by integers. Now, so we claim that this is a group. Of course, we've seen it fulfills all the 4 conditions. And we are also claiming that it will again fulfill the fifth condition, the commutativity property. And therefore it's an abelian group. Because if I take -2, -3, then add -2, this result is the same as -2 plus -3. And of course, this result is 5 in both cases. So it's commutative. So it's commutative. Now, so for you to tell if it's a group, if somebody was to ask you to tell if this is a group, then it means that person is asking you to go through all the axioms and show that they are fulfilled. For instance, you must show that there's closure. So you just take the example of this and show that there is closure, and then show that there is associativity, and then show that there is identity element 0 under addition, and then show that every element has an inverse. And then if you want to show that it's abelian, show that this commutativity property is satisfied. Now, the other example of a group is this set. What does this set mean? N is just an integer. N is just an integer. So what this means, if I take N and multiply by this, if I take N and multiply by this Z, what I come up with again would be a group. If I take N is an integer. Let me take, for instance, 2 and multiply 2 by this set. So I'll be getting 2Z. So 2Z will be, if I multiply by 2, I'll be getting even numbers. And this will be -6, -4, -2, 0, 2, 4, and so on. And again, we are claiming that this is another group because we can see there is closure. For instance, these are even numbers. So if I pick any two even numbers here and get their sum, the result will be even. If I pick any two even numbers and get their sum, the result will be even. That is to mean that the result will be a member of this set. The result will be a member of this set. Let me take -4 plus -2, and the result is -6, which is a member of this set. So, and you can see that every element has an inverse. 4 has its inverse here. 2 has its inverse here. 0 has the inverse of 0, which is just to be 0. So every element has an inverse. There is closure, there is associativity, and the identity element is there. So again, this is a group. So that is another example of a group. The other example of a group is the set of non-negative integers. The set of non-negative integers and addition. Now this one has, in fact, is not a group, not just an abelian group, but it's not a group. Because what I mean by set of non-negative integers is what I mean. It's not a group. Non-negative, it means it has no negative integers. So it could be having 0, 1, 2, 3, and so on. So it's not a group. It's not a group. It's not a group. No, leave alone even being abelian, it's not a group. And the reason is there are no additive inverses. So this one does not have inverses. There are no inverses here. This is what I mean by a set of non-negative integers. So it's not a group, not a group. Now let's look at this set and say whether it's a group or not. So I want to see whether this set is a group or not. Now I can see there are dots on the left side. That means that now those numbers continue to the left side to infinity. So what these dots mean that we have -6 is there, -8 is there, -7 is there, -9 all the way up to -1,000 is there. But on this other side, the last number is 5. So it has no 6, it has no 7, it has no 8. So the question is, does this set form a group and addition? Does it form a group and addition? Of course, I can see closure is satisfied. Not closure. I can see that there's identity element. Now, if you go to the left side, the closure will be satisfied, but I'm interested with the what on this side. If I take 4, for instance, then add 3, 4 plus 3, the answer will be 7. But 7 is not a member of this set. 7 is not a member of this set. So it means this set is not closed. This set is not closed. Even 4 plus 9, 4 plus 5, 9 is not there. 4 plus 5 will be 9. But 9 is not a member of this set. So not closed. It's not closed. So therefore, not a group. Not a group. So for you to disqualify it from being a group, just look for a reason that you feel, basing on those axioms, a reason that you feel disqualifies it from being a group. Now, the set of integers under multiplication. This is what I mean. This is a set of, we had already talked about this. This is the set of integers. And now, under multiplication, this set is not a group. Is not a group. Or is not an abelian group, there's no problem, but it's not a group. Because under multiplication, the identity element is 1. So I don't have an element which I can multiply by 2 to give me the identity element 1, for instance. I don't have an element which I can multiply by -3 to give me the identity element 1. So these elements lack inverses. And that's the reason I've given. It lacks inverses. Now, what about this set? What about this set? Is it a group? The question is it a group? And this one, you see it as it doesn't have a 0. So we want to consider it under multiplication and see whether it's a group. And you can see that it's a group under multiplication. Closure is satisfied if you pick any these elements and multiply. The result that you get is a member of the set. So closure is satisfied. Associativity is satisfied because if I pick these elements and add the same element of the group, the result will be the same as this. The result will be the same if I just change the position of the bracket. Every element has an inverse. 1 is the inverse of -1. -1 is the inverse of 1. And the identity element, of course, is 1. I have so many groups, so many types of groups. You'll go through those. Even we have the group of rational numbers. Rational numbers, these are numbers which can be written in the form A over B, where B is not equal to 0. That's what I mean by rational numbers. So what are examples of rational numbers? Like a half, a third, even 7. 7 can be written as 7 over 1. Even 8 can be written as 8 over 1. So that means What that means, when you talk about rational numbers, we are talking about all fractions. All fractions are rational numbers, and all whole numbers are rational numbers. So what therefore this means, when I talk about rational numbers, we mean something like 2, -2, -1, with all the fractions in between. With all the fractions in between. Even 0, 1, 2, 3, with all the fractions in between. So I mean things like a half are there, 2 out of 7, 1 out of 7, 3 out of 7, 1 out of 4, and so on. All the fractions are there. So what that means, this is a group under addition. Because it has the identity element 0, there is closure. For instance, if I multiply these two, I get 6, which is a member of this set. If I multiply a quarter times 2 out of 7, I'll get 4 out of 20, 2 out of 28, which is again a fraction here. It's also a fraction here. So closure is satisfied. Identity element is there. Every element has an inverse. For instance, the inverse of 3 is -3, which is here. The inverse of 2 is -2, which is here. The inverse of a quarter is -1/4, which is here. The inverse of 2 out of 7 is a -2 out of 7, which is here. So this set of rational numbers is a group under addition. Is a group under addition. The inverse is given by that. So that is also an example of a group. Now, what about if you remove 0? The set of non-zero rational numbers. If you remove 0, let's come back and remove 0. So when I remove this 0, does it become a group? Yes, but not under addition, because we've removed the identity, additive identity. So it becomes a group under multiplication. Because the inverse of a quarter is 4, which is here, under multiplication. The inverse of 2 is a half, which is here, which is a number here. The inverse of 3 is a third, which is among these elements. So again, that becomes a group under multiplication. So we have sets which will form groups under multiplication when you remove a 0. And if you return a 0, they form groups under addition. But we have other sets like the set of integers we saw above. It's just a group under addition. When you remove a 0, it does not become a group under multiplication. It does not become a group under multiplication because the elements would lack inverses. Now, we had talked about a set of matrices. Now, I'm looking at a special type of matrix here. This is a special type of matrix, which we call a general linear group of degree 2, and that 2, you're seeing it here. The elements are real numbers, and the condition is that the determinant is non-zero. The determinant should not be 0. So we are avoiding this determinant from being 0. The determinant of this product minus this product should not give us 0. So this type of matrices, if you have several of them together, that set, if you have several of them together, they'll form a group. But as earlier said, that group will not be abelian. That group will not be abelian. You have several matrices, 2 by 2 matrices, whose determinants are not 0. A set of those matrices put together would form a group, but that group will not be abelian. We already talked about that. And I've showed an example. I've taken I've said, let G be a group, let G be a set of A, B, C, D, where A, B, C, D are 2 by 2 matrices here. You can see this determinant is not 0. This determinant is not 0. The determinant is not 0. Does G form a group under multiplication? That's the question. So for you to do this, you have to show that there is closure. And then you have to show that there is associativity. Then you must show that there is an identity element. One of these groups is an identity element. One of these elements, you must show that it's an identity element. And then you must show that every element here has an inverse. Now, the easiest way to do this is to form a table. And that table, we call it the Cayley table. Oh, there's a Y here. Cayley table. Or just multiplication table, So this table, you take A, B, C, D, and take A, B, C, D. So we want to confirm whether closure is satisfied. So we want to multiply A by A and see whether we get an element, one of these elements. Multiply A times B and see whether you get one of these elements. Multiply A by C, multiply A by D, multiply by B by A, B by B, B by C, B by D, and see what you get. If you get anything outside these elements, then it means closure has not been satisfied. So let's just do that. I did that for you. I multiplied. I'll just take one. I'll just take one for as an example, and then you do the rest. I take A and multiply by B. So A by B, this is A. What about B? B is that. So when you multiply, we know how to multiply. It's a row and a column. So this row, 1 times 1 would be 1. And then 0 times 0 would be 0, of course. Then 1 times 0 would be 0. And then, so I'm multiplying this row by this column, then this row by this column. So 1 times 0 will be 0, and then 0 times negative 1 will be 0. Then I come to the last row, 0 times 1, then 1 times 0 will be 0. That sum. What about this? 0 times 0 will be 0, then 1 times negative 1 will be negative 1. So what is this? I've gotten 1 negative 1, so I've gotten B. I've gotten B. So A times B is B. So that's what I wrote here. A times B is B. Of course, A times A, when I multiply, I got A. Let me multiply B times C as the last example there, so that you'll do it later. You'll multiply it later. I wanted to multiply B and C. B and C. B is 1, 0, 0, negative 1. And then C is negative 1, 0, 0, 1. So when you multiply, it's a row and a column. This will be negative 1. Of course, I'll teach you how to do these matrices for those who don't know. But I suppose that we all know how to multiply. It's this row, and this column. The first one, the column, and you add the sum. So what I mean, it would be 1 times negative 1, and then 0 times 0, and that sum is negative 1. And then 1 times 0 is 0, and then 0 times 1 would be 0. That sum is 0. And then you come to the last row, 0 times negative 1 will be 0, and then negative 1 times 0 will be 0. So the sum again is 0. And then 0 times 0 will be 0, and then negative 1 times that will be negative 1. And so this again is negative 1, and this is D. It is D. So B times C is D. B times C, B times C is D. So you multiply all these matrices. When I multiplied all of them, every time I did, I got a member of the set. So A times A gave me a member of the set, A times B gave me a member of the set, A times C gave me a member. But what you also realize is that when I multiply A by any of these elements, I get those elements. A times B gives me B. A times C gives me C. So that means A is the identity element. A is the identity element. That's what it means. So a group has only one identity element, it cannot be several identity elements. So you will find that it's only A that has this behavior, that when you multiply it by any other element, you get that other element. Now, so from this table, closure is satisfied since multiplication of any two elements of the set gives an element of that set. So closure has been satisfied. So the other axiom is identity element is A. So we have shown two axioms. We have showed two axioms. Closure has been satisfied. The other axiom that we've showed is that there's identity element A, because we've looked at the behavior of A. Now, we already said this. We already said that if you have an element times its inverse, what you get is the identity. An element times its inverse, what you get is the identity. So that means the inverse of B is B, because B times B gives us the identity element A. So the inverse of B is B. The inverse of C is C, because C times C again has given us the identity element. What about the inverse of D? The inverse of D again is D, because D times D has given us the identity element. So every element has an inverse. What about the inverse of A? The inverse of A is A. The inverse of A is A, because A times A has given us identity element. So that is what I've explained here. So we've shown three axioms satisfied. The first axiom is closure. We've shown. The other axiom is the identity element. We've shown. And then the other axiom is that every element has an inverse, and again we've shown. So the last axiom that now comes automatically is associativity. Since we are dealing with multiplication, associativity will come automatically. So therefore, the set that was given to us is a group. This was the set that was given to us. So this set is a group. So the question is, but is it abelian? So that one is a question that you may want to go further and find out whether it's abelian. You may want to try by doing B times C and see whether it gives you C times B. You may want to try that and see whether it's abelian. Now, the set of complex numbers is also a group. What are complex numbers? Just want to define for you what complex numbers are. Complex numbers are numbers that can be written in the form A plus BI, where I is imaginary. Where I is imaginary and has the property that I square is -1. Has the property that I square is -1. So I is imaginary. So that means if you get the square root of I, the square root of I gives you, not the square root of I, the square root of -1 gives you I. The square root of negative 1 is I. So that if we have the square root of negative 4, square root of negative 4 is the same as the square root of 4 times the square root of negative 1, which is the same as 2 times I. So that is the square root of negative 4 is 2I. That means if you square 2I, you're supposed to get negative 4. Now, so that is the property of complex numbers. The complex numbers are numbers that can be written in the form a plus bi, where I is imaginary. So let me just give you examples that you can relate with, examples of complex numbers. A number like 3 is a complex number. All whole numbers that you know, are complex numbers, because 3 can be written as 3 plus 0i. Can be written like that. So it will have obeyed this property. Even 2 can be written as 2 plus 0i. So 2 is a complex number, 3 is a complex number, 7 is a complex number. 2 out of 7 is a complex number because it can be written like plus 0i. So negative 3 out of 4 is a complex number. So all the whole numbers that you know, all the fractions that you know are complex numbers. The other complex numbers are 2 plus I, 3 plus 4i. So you just combine. So they form groups and addition. They form groups and addition because if you have all these elements together, they would have closure will be there, associativity will be there, inverses will be there, and so on. What about when you remove 0 from them? So we remove a 0 by putting a star. I forgot to tell you that. You saw that example. So you remove a 0. When you see something that has a star, it means without a 0. If I write this, then I put a star there, then it will mean it lacks a 0. So when you remove a 0, it means you want to consider it as a group under multiplication. It means you want to consider it for a group under multiplication. Again, the complex numbers, you remove 0, then they become groups under multiplication because they would still have the identity element 1, and every element would have inverses, multiplicative inverses. And I've showed an example. There's an example here, example 56. Example 56. Let H be a set of complex numbers given by this. Is this a group under multiplication? Is H under multiplication a group? Is it a group? Is H under multiplication a group? So again, for us to do this, we use multiplication table as we did earlier. We have I, we have negative I, we have 1, we have negative 1, and we multiply by I, negative I, 1, and negative 1, just multiply. So I times I is supposed to give me negative 1. I times I, because we said I square is negative 1. I times negative I, this is I times negative I, which is the same as 1. Because this is negative multiplied by I square. But I square is negative 1. So negative 1 times this negative gives me 1. Then I times 1 will be I. And then I times negative 1 will be negative I. And then negative I times I, we already have that result as 1. Negative I times negative I, negative I times negative I, negative times negative will be positive, but I times I will be negative 1. I times I will be negative 1. and so on. So you just fill that table. In that table, I've already filled it for you. I've already filled this table for you. And so again, you'll see every time you multiply the elements of this set, you got an element of the set. You did not get anything outside this set. So it means this set is closed. So closure property satisfied. The identity element is 1 because you can see every time you multiply the 1 by -1, by I, you got I. 1 times negative I, you got negative I. 1 times 1, you got 1. 1 times -1, you got -1. So 1 has that property that it does not change the element you multiply with. It does not change it. You get that element. So 1 is the identity element. So that property is satisfied. The other property is the property of the inverse. And we've said the inverse of A is B if this product gives you identity element. If the inverse of A is B if this product gives you identity. So in other words, when I multiplied I by -I, I got the identity. So the inverse of I, therefore, is -I. That is the inverse. The inverse of I is -I because the product of these two gave me the identity. I want you to know how to get the inverse because we get a point where, of course, we already know how to get the inverse for modular. So that is easier. But in some other groups, this is how we get inverses. You know how to multiply. You must know how to multiply. The inverse of -I, when I multiply -I by I got 1. So again, it's true. The inverse of -I is I. The inverse of -I is I. The inverse of 1 is 1. Because 1 times 1 has given me the identity element. Yes, Amit? So that is about inverses. And you can see that the inverse of -1 is -1 because it gives you 1, the product. So that means every element there has an inverse. Now we are now familiar with this. We are familiar with this, the set of residues. What do you mean by residues? This is Zn. This is a set of Zn, which means Z mod n. Z mod n. For instance, we can talk of Z mod 3. When we talk of Z mod 3, we are dealing with the elements, the residues. Residues are, so the residue mod n are the numbers 0, 1, 2, all the way up to n minus 1. These are what we call residues. So for instance, when we talk of Z mod 3, then the residues are 0, 1, and 2. So this is the set we are talking about. Now when you talk of Z mod 8, then the residues are 0, 1, 2, 3, 4, 5, 6, and 7. These are what we call the residues. So what I mean is the set of these residues, therefore, is a group, and it's an abelian group. And addition is an abelian group. And how do we show that? Again, the same way we've done. For instance, here, we just add the elements. and we are adding it mod 3. This is 0, 1, then 2. We are adding it mod 3. So we know that when this is addition, 0 plus 0 will be 0, 0 plus 1 will be 1, 0 plus 2 will be 2. 0 is the identity element, so it has no impact on these elements. But now 1 plus 0 will be 1, 1 plus 1 will be 2, and 1 plus 2 will be 0. We are doing it mod 3. Mod 3, this is mod 3. And so 2 plus 0 will be 2, 2 plus 1 will be 0, and 2 plus 2 will be 1. We are doing it mod 3, and you know what that is. We are writing the remainder, of course, because 2 plus 2 was 4, and when we divide by 3, the remainder is 1. That's what we're writing. The remainder is 1, so that's what we write. So this is what we call the set of residues. The set of residues. So it forms a group. So that means Z4 would form a group, Z5 would form a group, and so on. Zn is a group. Under addition. Now, when we just remove a 0 from it, it doesn't form a group. When we just remove a 0 from it, for instance, when you remove 0 here, that you just have 1 and 2. Not form a group because there'll be no closure, there'll be no identity element. The identity element will not be there. So it will not form a group. But now, how do we make it a group when we remove 0? When we remove 0, to form a group, to form this class of residues to be a group, when you remove 0, you take elements which are inverse relatively prime to n and let them form a group. For instance, Z star 5. These would be elements 1, 2, 3, and 4. When I talk of Z star 8, to form a group, I would take elements which are relatively prime to 8, and these are the elements which are relatively prime to 8. And so it will form a group. And we already know what relatively prime is. We've met that word before, relatively prime. Now, so we can use Rust to give us this type of multiplicative groups and this type of additive groups, and that is what I wanted to show. That I can see that time is not on our side. So let's just look at this, and then maybe tomorrow we'll look at how Rust will assist us to form a group, to form these tables. Now, so Z5 has a 0. There is no star, so it has a 0. So let's just add again for the sake of those who don't know how to add. Let's add. These are the elements of Z5. Without Z5, if it has a 0, the residues are 0, 1, 2, 3, up to 4. So we just make those, the rows and that, and then we add 0 plus 0, 0, 0 plus 1 will be 1, 0 plus 2 will be 2, and so on. That is no problem. Then we add 2. 2 plus 0 will be 2. 2 plus 1 will be 3. 2 plus 2 will be 4. 2 plus 3 will be 0. And then 2 plus 4 will be 1. Of course, you know what I'm doing. When I added 2 plus 4, I got 6. Then since I'm talking about mod 5, then I get 1. And I divide by 5 and write the remainder. So you can see the elements I've gotten are elements of this set. So it means the set is closed under addition. Now, what is the inverse of 2? The inverse of 2 under addition is that element which, when you add it to 2, gives you the identity element 0. So that means from this table, I can see the inverse of 2 to be 3. Because, that means the inverse of 2, that's how I write it. -2 means inverse of 2 is 3. What is the inverse of 3? I can see again is 2. The inverse of 3 is 2. Element which when you add it to 2 to get the identity element. The inverse of 4 I can see is 1. So that 4 plus 1 gives the identity. Under multiplication, let's see. Now there's no 0. This is again Z5 star, where the elements are those which are relatively prime to 5. And these are the elements. So when you multiply 2 by 1 will be 2. 2 by 2 will be 4. 2 by 3 will be 1. 2 by 4 will be 3. Of course, that gives you 8, but we are doing it mod 5. Now, 3 by 1 will be 3. 3 by 2 will be 1. 3 by 3 will be 4. And 3 by 4 will be 2. Of course, that is 12, but mod 5. And so on. So the question is, what is the inverse of 2? Under multiplication, the inverse of 2 is that element multiplied by 2 gives you 1. So that element is 3. The inverse of 3 is that element multiplied by 3 gives you 1. Again, you can see the inverse of 3 is 2. And the inverse of 4 you can see to be 4. The inverse of 4 is 4. So that means Z5 star, Z star 5 is a group under multiplication. Closure is satisfied. Every time we multiplied the elements, we got members of the set. Associate, there is identity element 1. The group has identity element 1, and every element has an inverse. Every element has an inverse, and there is associativity. So again, it means there is a group under multiplication. So I also made another one here. You can try and multiply this. So this one is Z. This one is supposed to have a star. Supposed to have a star. Z star 15. Z star 15. So this is a set comprising of elements which are relatively prime to 15. Elements which are relatively prime to 15. These are the elements which are relatively prime to 15, and they should be less than 15. Elements which are relatively prime to 15 and less than 15 are here. So then now you just multiply. 2 times 8 will be 1. 2 times 14 times 11 will be 7. Of course, that is 22 mod 15. 22 mod 15 is 7. So you just do multiplication. 11 times 4, you get 14. And you know how to do that. So again, you notice that every time you multiplied 2 elements, you got elements of this set. And you can see that every element has an inverse. For instance, the inverse of 7, you can see is 13. The inverse of 7 is 13, because they give the identity element. You can see the inverse of 11 to be 11. You can see the inverse of 14 to be 14. And of course, we had learned how to get those inverses. But if you have this table, you just look at the table, this multiplication table, and you are able to see the inverse of those elements. So I think tomorrow what we do, I'll then be giving you the code that will be giving you those tables, both additive and multiplicative tables. Thank you.
Thank you, everyone. Let's meet tomorrow, 12 p.m. East Africa time for the online bootcamp. Thank you, Simon. You can end the session.